Finally, we can talk about how do we actually draw anything of interest. So far we've set up buffers, we've set up windows, but we don't have any geometry to actually appear on the screen. This is what we're going to discuss in the current segment. OpenGL provides a large number of primitives: points, lines, polygons, triangles, quads, quad strips, triangle fans. The strips and fans are just more efficient ways of specifying primitives. If you have multiple triangles that share vertices, you can describe them with fewer parameters. So in a triangle strip, you have these three vertices defining a triangle. The next triangle shares two of the vertices, and so you need to define only one new vertex for it. So essentially, you have one new vertex per triangle. In the triangle fan, there's a central location, and then you define the vertices around it. So you can define points with GL points. We'll just talk about GL begin, GL end, newer ways of specifying geometry. It's stored in homogeneous coordinates. You can define line segments using GL lines. Polygons, the one assumption is that these are planar convex polygons, and simple also. Even concave polygons are a bit hard. For more complex shapes, I would suggest you tessellate and use GLU has some utilities. We've already talked about strips, loops, triangles, fans, quads, and ways in which of handling them. GLUT introduces a few additional primitives, and in fact we've used the GLUT primitives in homework 2 so that you don't have to bother too much about instantiating geometry and you can focus on the lighting and shading, which is what homework 2 is about. So the GLUT 3D primitives are a cube, sphere, and teapot, and indeed these are the primitives that you will be using in homework 2. OpenGL drawing has gone through an evolution. I'll talk first about the old OpenGL way of drawing, which many students actually feel is easier to understand and easier to use. And then I'll talk about the modern way in which OpenGL drawing is done using Vertex buffer objects. Note that both methods are currently supported. It remains backward compatible. However, they do encourage the new method, but it's not required. In old OpenGL, you have the client-server model. The client encloses the list of vertices between a GL begin and GL end pair. Moreover, you can include normal C code. So for example, if you want to compute the vertices on a circle, you can use sines and cosines. Inside are commands like GL vertex 3f and GL color 3f. What is the 3f for? It's really because OpenGL is C-based. Remember, it dates back to 92. It doesn't include function overloading. So 3f means it's a floating point arguments, 3 of them are input. If it were 3i, it would be 3 integer arguments, and it defines different functions for each of these. One thing that people often get confused with is they say, I define a vertex, I define color, vertex color. Let me just write this down. So I can say GL vertex, and then I can define GL color after that. This is a common mistake. You should not do it in this order. So what you think is I've defined the geometry and then I've defined the color, and this color should be associated with this vertex. In fact, per OpenGL conventions, this is wrong. And what you should really do is define the color before you define the vertex. The reason for that is that old style OpenGL is really a state machine. Therefore, what needs to happen is that it reads the current state, and you need to set the state before you call the GL vertex command. It's really an assembly line. You pass the vertices, OpenGL takes them, transforms them, shades them, and all of that processing is currently what you can program in the vertex and fragment shaders in the GPU. This is immediate mode, where the data you put out is immediately handled by OpenGL. The retained mode is where it's retained so it can be reused and optimized. In fact, the modern OpenGL of Vertex buffer objects is essentially trying to develop a fast, efficient retain mode algorithm. Continuing on with old OpenGL, this is what the drawing in display would look like if you want to draw a polygon. And in fact, this is essentially the code that I used before I switched to more modern OpenGL to draw the plane in that I've just been showing you in the demos. So what we say is display, clear the color buffer bit, And then I define the color. So I define the color red, and I put it at 0.5, 0.5. Incidentally, this is a useful debugging trick. If you just draw a plane, you may not know which vertex in your code is where in your screen. But if you give them each colors, it's very obvious, and OpenGL will interpolate the colors. And so this is a nice way of labeling the vertices in the scene that you're drawing. So this is 0.5, 0.5 is red. Then you can go to the next one, which has color green, means minus 0.5, 0.5. And you go through, so you have color blue at minus 0.5, minus 0.5, color white. Note that GL color always comes before GL vertex. Then GL end means that within that block you're specifying the geometry. And flush is just a synchronization command to send the commands to the server, flush the queue. So old style OpenGL operates in this client-server model, even though in practice the client and server are almost always on the same computer. And so GL flush forces the client to send what could be a network packet, but it's usually just an internal synchronization. GL finish waits for the ACK and should be used sparingly. That's all that I have to say about drawing in old style OpenGL. You can specify the type of object you're drawing, GL polygon, GL triangle, so on. New OpenGL defines these new concepts known as vertex buffer objects that are more elegant and more efficient. We have included examples of them in the demo code we provide. At the same time, I do want to say that they are more complicated, and if you're writing your first OpenGL programs, you may want to start with old style OpenGL. So here is the floor specification. I've just defined a number of arrays which contain various types of information. So here is the floor vertices. So I have 4 vertices, each of which includes 3 coordinates. These are in inhomogeneous coordinates. I have floor color for each of the 3 vertices, and again, red, green, blue, white. Then I have the floor indices. So I want to consider 0, 1, 2, and 3, which is just one polygon. And then I have the floor vertices, which is a definition of the second object. So that's why I've called it floor verts 2. So remember that I actually do have 2 planes, although we'll be focusing on the first one. And similarly, I've defined floor color 2 and floor indices 2. So here is what I do to set up the vertex buffer objects. The number of objects is 2 in this case. The number of buffers per object is 3. So vertices, colors, and indices. Indices is just a pointer to the vertex. Instead of saying draw from vertex 1, 1, 1 to 2, 2, 2 to 3, 3, 3, I just define the vertices first, and then I say connect vertex 0 to vertex 1 to vertex 2 to make a triangle. It's a very standard way of doing things. So the buffers per object, list of buffers for the geometric data, and then you have objects. And so defining a number of different arrays. Primitive type is the type of primitive, quads, polygons. And the number of elements is the number of geometric elements, whether they're triangles, quads, etc. Now we also have this buffer offset macro, and this is discussed in the OpenGL Red Book. It ensures that we can offset certain number of bytes. We don't have to worry about it. Similarly, we have the number of array macro, again taken from the Red Book, which is just how many numbers does this array have. I have defined vertices, colors, elements to define the 3 arrays, and floor and floor 2 for the objects and on the scene. Here is my actual program, and I'll go over it in detail. First, I define my offset as object times num per obj, and that's just because different objects are stored differently, and multiplying these together ensures I get the correct buffer number. Thereafter, I have to bind the buffer. So this is an array buffer, and I have to bind it with the appropriate buffer. So in this case, it's vertices. So let me just consider that. And so here I'm talking about vertices. Then I have to define the data in the buffer, which is size of the number of vertices, and vertex, and GL static draw is just a command which tells the system how to optimize things. All right, so then I define a GL vertex pointer into the buffer, and this is 3 variables. They're a floating point type, and then I have my buffer offset into the buffer. And then I enable the client state of the GL vertex array that enables it to be drawn. Okay, then the second thing is I bind the buffer with the colors, go through the same kind of analysis, define the color pointer, enable the client state. The final step is perhaps interesting. So I define the GL element array buffer. So now that's not an array, it's an array of elements. So that's the indices like 0, 1, 2, 3. And again, defining it appropriately. I set the primitive type of the object to the type. So that's triangle squad, and the number of elements on the object to the number of indices or the number of faces. And this is a command to initialize the buffers. Of course, this is, I realize, fairly complicated, and it's just the standard syntax that's used in OpenGL. And I've given you an example of the code so that you can build off it. Having defined the buffers, we also need to draw the vertex of it, object. And once we've defined the data in the buffers, the code is actually very similar. I bind the buffer appropriately, and essentially that's what I need to do. So the only difference really from the code you saw previously is that I don't specify the buffer data that's already available to me. And so you see colors, I'm binding the buffer for the elements. Now what do I do inside the void display? I call draw object for floor and floor 2. And notice this final command that actually does the drawing. So it's GL draw elements. It takes the primitive type for the object, whether triangles, quads, the number of elements, and it goes to the appropriate buffer. So the buffer has been bound to the elements. All of this is essentially just standard syntax in OpenGL for drawing. It may be a bit confusing to understand, but we've given you the sequence of commands so that you can build on it. Let's talk about initialization for drawing and shading. So I've defined a vertex shader, a fragment shader, and a shader program. And these are important to the initialization. So what I first do is call this glGenBuffers command, and it generates a number of buffers equal to number per object times the number of objects. I initialize the objects for floor and floor 2, and then I call the vertex shader, the fragment shader, and the shader program. We'll be talking more about the different steps in setting up an OpenGL shader later, but for now this init shaders just returns a number for the vertex and fragment shader, and the shader program essentially links them together. So it takes the vertex and fragment shader and makes a shader program. Notice that I have here file names. So let me just draw this, fragment shader and vertex shader. So the fragment and vertex shaders live in files that are at these specific locations, and in fact they're compiled on the fly. So you don't need to recompile your program if you change the vertex or fragment shaders. Having shown you all of this code, it might be more instructive that I actually do a demo of changing colors. It's actually very easy, so let me bring in my text window where I have the code. And here I have the floor color. So this is red, green, blue, and white. What I'm going to do now is that I will comment this region out. So let me copy it. I'm just showing you all the steps involved, just so you get a sense that this is real code that I'm going to write here. So I will go ahead and comment out the earlier line. And now I'm going to change the color. So for example, I could make this all white. So let's make it all white. And if I do this, I should get a completely white floor. The final one is already white. So let me save this file. And you may have a number of different compilation environments, but I'm running this on a Mac, and I'm just using make. So it runs the make file, and notice that there are a few different definitions, GLGX prototypes, the OSX, and all of these things are of course specified for you in your make file. You already have the compilation environment set up. So now I can run the program myTest1, and let me bring it in here. Notice that the plane on top is still the same, so that hasn't changed, but the plane on the bottom is now white instead of being multicolored. And I still have the same interactions. I can zoom in and zoom out. I can press escape to quit, since I have that in my keyboard routine. And if I now change back to the colors, it would go back to being multicolored. So let me just comment this out and I'll change it again. Not necessarily a very exciting demo, but it's a first step showing that you can write these type of programs. Now you can see that it is in fact multicolored, the plane, because it has 4 different colors and they're interpolated.